Dear students, now let us discuss about the third and last module, that is algebraic backgrounds. So in this module, we will discuss about the algebraic number theory. And so what is an R module? You know that. Already you studied what is a group, a ring, module, submodules, question modules, etc. and so on, as well as free abelian groups and so on. What is actually an R module? R module means, suppose R be a ring, let R be a ring, then an abelian group M. What is an abelian group? It's a commutative group. An abelian group M with a written additively together with a function alpha from R cross M to M. What is R? R be a ring. Such that alpha of Rm equals Rm, alpha of Rm equals Rm for all R fall in R. It has the following properties: R plus S into M, where R and S fall in R. R plus S into M equals, it is Rm plus Sm. R, S are present in R. Again, R into M plus N. R into M plus N equals Rm plus Rn, where M and N fall in M. Agreed. Then R into Sm equals Rs into M, where again R and S presents in R. Moreover, 1 into M equals M, for all M fall in M. If any M satisfies this property and R is the ring, then it is written additively together with a function alpha from R cross M to M satisfies these properties. Then M is called an R module. Here the function alpha is said to be R action on M. Alpha is known as R action on M. Agree? So by using some arguments in algebra, you know that. What is a submodule of M? If N is a submodule of M, if M is any R module, then N is a submodule of M when N is a abelian subgroup of M. N forms a subgroup as well as N is an abelian group, then N is said to be a submodule of M. Now, what is the quotient module? If M and N are any two modules and N is a submodule of M, then the quotient module is written as M by N, and any element in M by N is of the form sum M plus N, where for all M fall in N. Sorry, M fall in M, not N. M presents in M. So this is the expression of elements in R module M by. Okay, so this M by N is said to be a quotient module. This is said to be a quotient module. M by N exists only when N be a submodule of M. The quotient group M by N exists when N be a subgroup of M. So in the light of that argument, M by N is a quotient module when N be a submodule of M, and the elements in M by N is expressed as M plus N, where M fall in M. Okay, so consider the R action on M, that is alpha from R action on M by N is alpha from R cross M by N. Consider the function R alpha from R cross M by N to M by N. By it is defined as alpha of R comma M plus N. An element in R cross M by N is expressed as element in R is R and M by N is of the form M plus N equals R into N plus M plus N. R into M plus N is, it is Rm plus N. So any element in M by R cross M by N is expressed in ordered pair R and M plus N. Then the R action on M by N is alpha from R cross M by N to M by N by alpha of R M plus N is Rm plus N. Agreed. So this is the submodule and the quotient module. M by N is a quotient module only when N be a submodule of M. Agreed. Now, what is a set module? Next, set module. Set module means, set module is nothing but an R module. Set module is nothing but an R module. It is more than an abelian group M written additively. That is, for a given abelian group, suppose M is an abelian group. M is an abelian group. M is an abelian group. Then this, we can make it as a Z module. How to make this M as a submodule? By defining it is 0 into M equals 0 for all M fall in M. 1 into M equals M for all M fall in M. Okay. And N plus 1 into M. N plus 1 into N equals Nm plus M. Moreover, minus N into M equals minus Nm, where N is any integer. Okay. So, then you can convert or you can make a abelian group to a set module by defining this way. Agreed. So, set module is nothing but an abelian group, then return S additivity. Okay. So, if M is an abelian group, then we can make it as a submodule by defining this way: 0 into M equals 0, 1 into M equals M, and N plus 1 M equals Nm plus M, as well as minus N into M equals minus N. Okay. Now, what is free abelian groups? What is free abelian? Let G be an abelian group. G be an abelian group. Then, G is finitely generated. What is finitely generation? G be a finitely group and G be a finitely generated as a submodule. Means there exists some G1, G2, etc. some Gm fall in G. Okay, fall in G. Then suppose G is any element in G. Then this G can be written as the linear combination of these Gi's. That is G equals M1, G1 plus etc. plus M Gm or Mn. Mn Gm. Mn into Gm or Mn into Gn. M1 G1 plus etc. plus Mn Gn means G, any element in G can be expressed as a linear combination of the elements G1, G2 etc. Gn. Then G is said to be finitely generated by this G1, G2 etc. G. Agree. Finitely generated, where this Mi, what is this Mi? Mi's are integers. So a group G is said to be finitely generated if any element in that G can be expressed as a linear combination of this Gi, G1 etc. G. Now, if these Mi's are zeros, consider this linear combination M1 G1 plus etc. plus Mn Gn equals 0. If all Mi equals 0, then these Gi's are linearly independent. So moreover, if G is spanned by this G1 etc. Gn, spanned means that's a linear combination. If this G can be expressed as a linear combination of this G1 etc. Gn, as well as this Gi's are linearly independent, then this G1, G2 etc. Gn are said to be the basis. They are called the basis of G. Okay. So a linearly independent set which generates G is called its basis. Okay. Now, what is a free abelian group? A free abelian group. Free abelian group. What is free abelian? Free abelian group means an abelian group with a basis of n elements called a free abelian group of rank n. The term is rank n. A free abelian group, let G be a free abelian, let G be a group, a free abelian group of rank n if G has a basis consists of n elements. G1, G2, etc. Gn presents in G. All of this, if any element in G can be expressed as a linear combination of these Gi's, moreover this G1, G2, etc. Gn are linearly independent, then the set G1, G2, etc. Gn is said to be a basis of G. Thus, this G be a free abelian group with the basis G1 etc. Gn, then is of rank. It is called a free abelian group of rank n. Okay. Now, if GBA, let G be a free abelian group of rank n. G be a free abelian group of rank n. So let X set of all x1 etc. xn, comma set of all y1 etc. yn are the basis of G. Let x1 etc. xn and y1 etc. yn are the basis of G. Then there exists some integers aij and bij. Let aij and bij are integers, aij and bij's are integers, such that this yi is sigma with respect to j, aij yj, sorry, aij xj. Consider this yi. So yi equals sigma with respect to j, aij xj. And consider xi. Xi equals sigma with respect to j, bij yj. Consider these linear combinations. So means yi, any element in yi presents in where xi is x1 etc. xn, y1 etc. yn are the basis of G. Then any yi can be expressed as a linear combination of xj's as well as xi's are the linear combination of yj's. So consider the matrices A equals matrix aij and B equals matrix bij. A equals matrix aij and B equals matrix bij. Then it follows that A into B, AB equals In. AB is A is an n by n matrix, B is also an n square matrix. So the product AB is also an n square matrix such that AB equals In. In means nth order identity. So what is determinant of AB? Determinant of AB equals determinant of In. Determinant of In is 1. Determinant of an identity matrix is always 1 irrespective of the order. What is determinant AB? Determinant AB is determinant A into determinant B. Determinant A into determinant B. So determinant A into determinant B is 1. But we know that this aij and bij are integers. So what is aij? A is matrix aij means all the entries in A is integers. Okay. All the matrix, all the entries of A are integers as well as all the entries of B are also integers. Since A and B are the matrices whose entries are integers, we know that determinant A is an integer. Determinant A is an integer as well as determinant B is also an integer. Since the entries in A and B are integers, hence determinant A is also an integer as well as determinant B. So, but here the product of two determinants, determinant A into determinant B is 1, means the product of two integers are 1, then that means there is only the possibility determinant A equals plus or minus 1 and determinant B equals plus or minus 1. Okay, so you can choose this aij and bij. If x1 etc. xn, y1 etc. yn are the basis of a free abelian group G, such that yi equals sigma with respect to j aij xj and xi equals sigma with respect to j bij yj, where aij and bij are integers, then you can construct the matrices. A is a matrix aij, B is matrix bij with a AB equals In. Since A and B are the matrices having integer entries, then determinant A and determinant B are also integers. But we know that when AB equals In, determinant AB is determinant In, determinant of an identity matrix is 1 irrespective of its order, then determinant A into determinant AB is 1, but determinant A and determinant B are integers. Hence, from here we know that determinant A is plus or minus 1 as well as determinant B is plus or minus 1. So we consider a matrix, a square matrix whose determinant value is plus or minus 1 is said to be a, we know that it is that matrix is said to be a unimodular matrix. Clear? That A is an n square matrix with the determinant A is plus or minus 1, A is an n square matrix. Consider matrix A. A is an n square matrix with the determinant A equals plus or minus 1, then A is said to be a unimodular. A is said to be a unimodular matrix. Okay. So, now with respect, as it depends upon this definition, we tries to prove a lemma. Consider the results. The lemma states that let G be a free abelian group. G be a free abelian group. Let G be a free abelian group of rank n. What about its rank? Rank is n. Means G has a basis consists of n elements. Okay. So with the basis x1 etc. x. With the basis x1 etc. x. Suppose AHA is an n by n matrix. A equals AHA is an n by n matrix or n square matrix with an integer entries. Means AHA following such. A equals AHA is an n square matrix with the integer entries. Then the elements yi. Then the elements yi equals sigma with respect to j aij xj forms a basis of G. This forms a basis of G if and only if matrix A or aij, matrix aij is unimodular. Matrix aij is unimodular. How to prove this one? So for its proof, the necessary arguments. First, suppose that G be a free abelian group having rank. G be a free abelian group of rank. Means this G has a basis which consists of n elements. So let x1, x2, etc. xn be the elements with a basis. It is given set of all x1, x2, etc. xn be a basis. Let set of y1, y2, etc. yn be another basis. Another basis. Why? Because its rank is n. The base consists of n elements. Then there exist integers a, I, j. We already said that a, I, j and b, I, j are integers such that come on, yi equals sigma with respect to j aij xj and xi equals sigma with respect to j bij yj. Okay, right. So let A equals, we can construct a matrix. A equals matrix A. It is given A is aij is an n square matrix having integer entries as well as, and B is another matrix. B equals matrix bij. It's also an n square matrix with integer entries. In such a way that AB equals I. You can construct A and B in such a way that AB equals I. Then we know that AB equals IN means, we know that from the previous dots we have determined A equals plus or minus 1 when AB equals IN. Then determined AB equals 1, but A and B are matrices having integer entries. Thus determined A into determined B equals 1 has only possibilities. Determined A is plus or minus 1 or determined B is plus or minus 1. Determined A is plus or minus 1 means the matrix Aij is unimodular. That is what we requires. Okay, this is the first part. Clear? Okay. What about the reverse inclusion? For the reverse inclusion, consider, let for the reverse inclusion, suppose matrix A is the given matrix. A equals matrix Aij, that's an n square matrix which is unimodular. which is unimodular. Now to prove that the G be a free abelian group of rank n. Since A is AIJ is unimodular, that means determinant E, determinant A means determinant of AIJ equals plus or minus 1. Okay. So, determinant A is plus or minus 1 means, what is determinant E? Means determinant A is plus or minus 1. Determinant A is plus or minus 1 means determinant A is strictly differs from 0. Okay. Determinant A strictly differs from 0. So, we have the linear combination. What is the linear combinations? We have xi equals sigma with respect to j, or ya equals we have ya equals sigma with respect to j aij xj. Since a is a determinant of a differs from 0, aij are integers. Determinant a differs from 0 means, what is ya? Linear combination of xj. So this yj's are linearly independent. Okay. Determinant a differs from 0 means this yj's are linearly independent. But what is A inverse? We know that A inverse equals 1 by determinant A into adjoint of A. A inverse equals 1 by determinant A into adjoint of A. So, what is determinant A? Determinant A is plus or minus 1. So, this implies A inverse equals plus or minus of matrix adjoint A. A equals plus or minus of adjoint A. But what is A? A is a square matrix having integer entries. For A inverse is also having integer entries. So, A inverse are also integers. Let B equals, the matrix A inverse is renamed as B. B equals A inverse. So what is A inverse? What is B? Matrix Bij. So matrix Bij equals A inverse. That means xj equals sigma with respect to j Bij yj. Okay. That means every element in G can be expressed as a linear combinations. Therefore, G be a free abelian group of rank n. That is what we require here. Agree? Okay. Thank you.